Okay, thank you very much. And I will go quickly to try not to delay your lunch by too much. First, I'll thank the organizers for the opportunity and the honor of being able to speak here. And what I want to tell you about, I must be slightly apologetic. Doesn't have much holography in it. In fact, on the face of it, none. Although there are some interesting questions which could potentially be holographic. For example, the story I want to tell you, one could presumably lift it to talk about n equals 4 amplitudes, which is a big science, and holography is of interest there, gauge gravity duality and actually understanding how they work at strong coupling. But that has not been done yet, at least not done well enough for public consumption. So I'm going to give you more of the basics, which is ordinary field theory. Field theory in 4 dimensions specifically, and actually mostly focused on electrodynamics. So the infrared sector of quantum electrodynamics and perturbative quantum gravity, by the way, have recently been of some interest in discussions about potentially resolving the black hole information paradox. These discussions revolve around some rather interesting large gauge transformations and new symmetries of both theories, both QED and perturbative quantum gravity. And in fact, this study brings up quite a few interesting fundamental issues, which one can pull back to these field theories even in the absence of black holes and ask interesting questions. And that's actually what I want to do here. So what I'm going to do is come back to quantum electrodynamics and take a really simple but somewhat more information theoretical look at the infrared than perhaps what has been done before. And I will talk about perturbative quantum gravity. It is very similar, the infrared problem, to electrodynamics. The results are a little more powerful because everything is charged under gravity, whereas for electrodynamics, it's only actual charged particles. On the other hand, perturbative quantum gravity is not such a well-defined quantum field theory. It's not renormalizable. Imposing cutoffs and so on do have some conceptual problems, so it's not quite as well developed as QED, although perhaps the blanks could be filled in with some hard work. So quantum electrodynamics is a beautiful physical theory, purportedly the best theory in science, makes incredibly precise predictions. These predictions are in some cases confirmed by incredibly precise experiments. Its perturbation theory is rapidly converging. So for example, if you want to know the amplitude for some elementary process, like molar scattering, for example, to the 1% level, you simply write down this Feynman diagram and use it to calculate the amplitude, which means amputate legs, put on wave functions, and so on. That doesn't even involve doing an integral. It's just algebra, so it's something very easy and from a quantum field theory textbook. And the perturbation series, to correct it, is very convergent. Well, actually, it's not convergent. It's an asymptotic series, but expected to converge for the first 100 orders or so. And each order is down by a factor of 100, or up by a factor of 100 in accuracy. And so this is a very good and, in some sense, exactly solvable theory. So for example, if 1% accuracy isn't good enough, but you want 0.01%, what you do is you take this amplitude and loop correct it. The loops pose an immediate technical problem. One of them is that internal loops like this is ultraviolet divergent. That's, of course, something we know how to handle with renormalization theory, and really one must do renormalized perturbation theory and is not a problem. The other one is a loop like this specific one I've drawn here is also infrared divergent. Infrared divergents are not removed by renormalization. One must do something else. They are actually something physical. What you're supposed to do has been known actually since the early days of QED, since before renormalization of ultraviolet divergences was understood. What you're supposed to do is take this, which is divergent when the photon has very small energy and momentum, and recognize that it's almost the same as this process, where this photon actually becomes physical, but is so soft, in other words, has such small energy and wave number, that it's virtually undetectable, in that the energy it carries away is so small that it perhaps doesn't disturb the kinematics of the rest of the process. And if you sum over, when you calculate probabilities, the probability of this happening, it also has an infrared divergence in it, which cancels the infrared divergence and the probability of this happening. In fact, it looks a lot like this, that when you actually calculate probabilities, the probability of emitting this extra photon summed over the ultra soft photons cancels the divergence coming from the cross term between two processes in this term. And of course, this is textbook quantum electrodynamics. In fact, even old textbooks from the 1950s spell this out very nicely. And this calculation, this cancellation, I should say, is known to happen order by order in perturbation theory. And as in fact, it's guaranteed by unitarity, because of course here you can think of this as the T star T, the T matrix squared, and this is calculating the imaginary part of the T matrix, and the cancellation is just due to the optical theorem. So that's all very nice, but it tells us something about the physics of what's going on when you talk about Moeller scattering. And that's that this nice process here, which was good to the 1% level, isn't really what physically happens. What physically happens is something more like this: the emission of a large and, in fact, an infinite number of soft photons during the scattering process. And that's simply because this has much more probability than this. This probability is greater because, well, because of the infrared divergence as in summing over the photons that emerge. Mathematically, there's a cancellation between the probabilities of these and things like this. So mathematically, this is a good thing to compute, but physically, in a sense, this is what is happening. And this story dates back many years to the early days of quantum electrodynamics, and and is encoded in what are known as soft photon theorems, which also a very long time ago were generalized by Weinberg to talk about soft graviton theorems, where the story is very similar. So the question I want to ask here is, if physically this is a process, and anytime two things scatter, a whole bunch of soft photons fly away. Those soft photons, well, they're quantum mechanical particles. They have quantum states. You need a considerable amount of information to specify their state. They don't have much energy, but they have a direction of motion. They have a polarization, and so on. So when they fly away undetected, how much information do they carry with them? And this question is addressed in a series of papers by us. The first one with Gianluca Grignani, and then with Dan Carney, who was a postdoc in our group and is now in Maryland, and my two excellent graduate students, Laurent Charret and Dominic Neuenfeld. And it's in particular the first of these papers that I'll tell you about, and probably we'll have time to only briefly mention the other two results. So let me try and be extremely explicit about what I mean by losing information when you lose track of soft photons. So let me do that in the context of a simpler model. Say I take a simple 2-qubit system, say qubit 1 and qubit 2, and assume that they're not dynamically related. So even energy eigenstates can be written as a direct product of the two. So the Hilbert space is simply a product of 2 qubits. And say the qubit states could be spin up and down like simple qubits. And what I want to answer is a question is if I lose track of qubit number 2, so it gets lost somewhere. So here's qubit number 1 and qubit number 2. It's backwards for me. And say I have them here. They're my interacting stuff. Qubit number 2 is soft photon, so it flies away. Qubit number 1 is left. How much information did I lose about qubit number 1 when qubit number 2 went away? What do I not know about it now that I might have known about it before? In the classical world, the answer is 0. I can still do any measurements I like on qubit number 1, and the information is all there. In the quantum world, on the other hand, it depends a lot on the state of the system at the time when they flew away. And so let me consider 2 examples. One I'll call an unentangled state, which can be written as a direct product of a state of qubit 1 and qubit 2 in a simple way. And the other one, an entangled state, which cannot be written in such a direct product, but qubit 2 still enters fairly simply. Now, when qubit 2 gets lost, is gone, and I want to do measurements, quantum measurements I will do with projection operators because I'm a theorist. Those projection operators on the lost qubit, on number 2, can only operate as the unit matrix on its Hilbert space. So I can take into account all possible such measurements by simply contracting the wave function with the unit matrix, or by taking this density matrix and tracing out the degrees of freedom of number 2 to make a density matrix for the degrees of freedom of number 1 only. When I do that in these 2 example states, you can see that the result is slightly different. Not a lot different. In fact, the 2 example states I've organized so that the expectation values of spin up and spin down for qubit 1 are the same in the 2 states. And you can see that in the diagonal elements of the density matrix, which I'll show you on the next page as a matrix. The diagonal elements are the same. What have I lost in the case where they were entangled as opposed to unentangled? Well, unentangled is actually still a pure state. Right? When I lost qubit 2, qubit 1, well, it was in a pure state to begin with and remains in a pure state. So in some sense, I've lost no information about it. Whatever I could extract by clever measurements on qubit 1, I could still do here. And basically, the results should be the same as they were before qubit 2 flew away. In the entangled state, well, there's a little bit of a difference here. And the difference is that the off-diagonal elements of this density matrix have gone to 0. Okay, so the density matrix is different, therefore the physics is going to be different in some way. Exactly how is it different? The so what I would like to answer here. Well, if I make a measurement of the spin up or spin down probability for qubit 1, there's actually no difference. Right? They're still the same. They're this diagonal element of the density matrix, so the lower one. I have to be a little bit more sophisticated to see the difference. I have to measure something which measures the off-diagonal components. So say the probability that the spin of qubit 1 is polarized in the x instead of the z direction, or is a superposition of 2 spin up and spin down, something like that. Then I can see in the unentangled state, the probability is something like this. In the entangled one, it's something like this. The difference between these two is actually the cross terms here, which is the interference terms. So what I have lost is a possibility of interference. In the entangled case, this probability is more like a classical one. It's just the content of this guy in the spin-up wave function times the probability of spin-up plus the content in down times the probability in spin-down. So it's like a classical distribution, whereas this one still has the possibility of quantum mechanical interference. And so it's interference that one loses. So so that's the difference between having the states initially entangled and unentangled. This difference can be quantified, or the amount of entanglement can be quantified in something called the entanglement entropy, which is simply the von Neumann entropy of the reduced density matrix. So in the unentangled case, the entanglement entropy is 0, and the entangled case, it's non-zero, and is simply given by something which depends on the details of the diagonal, well, of the eigenvalues of the density matrix. Okay, so let me pull this story up to quantum electrodynamics in the following way. Actually, a lot of my work in this field came from trying to understand entanglement entropy in quantum field theory in momentum space. This was one of the ways that one could make it work. So let's, that is in entanglement entropy that's generated by the S matrix. So let's discuss a little bit how that works. So let me consider a scattering experiment where I have an in state which goes to an out state, and that out state is some superposition of in states, and the coefficients in the superposition are the S matrix. The in state I will call a state with hard particles, so a high energy electron or a photon that's well above some infrared cutoff. And the out state is generated by the S matrix, can contain both hard and soft particles, and I'll call the soft particles gamma. And here my hard particles are electrons which are massive or energetic photons, and the soft particles are only photons which have small energies, say below some infrared cutoff. Now in quantum electrodynamics, the S matrix is infrared divergent. So this formula only makes sense if I introduce some fundamental cutoff on the S matrix, fundamental infrared cutoff. So a very nice way to do that is just to give the photon a small mass. That ruins gauge invariance, of course, and there's some other unsavory features of doing that, but it is a unitary theory still, and still Lorentz invariant, so in some ways it's quite convenient. So let me assume that the photon has a very small mass and use it as an infrared cutoff. Then this equation makes some sense, and I will write the cutoff as a superscript on the S matrix from now on. Okay, so take the out state that one gets and make this density matrix-like state. So then how do you sum over inclusive amplitudes where you produce soft photons? Well, take this density matrix and simply trace it over the soft photons to make a reduced density matrix. So this is a density matrix that you will use to answer questions about after your scattering experiment is done. A bunch of soft photons escaped detection and flew away and will never be seen again. The density matrix that answers questions for the stuff that remains behind will be this one, which, where the soft photons are traced out. The diagonal elements of this density matrix are just the good old probabilities of quantum processes that one calculated in quantum electrodynamics that particle physicists have computed for the last 60 years or however long electrodynamics has been with us. But the off-diagonal elements are what are, by my previous argument, of interest to us here. And so one can ask the question, what about off-diagonal elements here? What does this density matrix look like in the off-diagonal? And this is something you will not find in the electrodynamics textbooks. And so one might wonder if the answer